Hey class, let's continue the discussion of isomorphisms that we started last video. So to remind you, last video we learned what it means to have an isomorphism, which is a particular type of function from one group to another. Now let me add one bit of terminology to that story, which is sort of the adjective version. What does it mean to say that two groups are isomorphic? If G and H are two groups, then we'll say G is isomorphic to H, which is written with this symbol I've drawn here, if there exists some isomorphism phi from the group G to the group H. So the philosophy that I want to sort of slowly start to convince you of in this video is that if G is isomorphic to H, then that's kind of a fancy mathematical way of saying that G and H are somehow essentially the same group. Let's think about a specific example to see a little more about what I mean by that. So in last video, we proved that the group Z4 was isomorphic to the group U4 of fourth roots of unity. And remember, how did we prove that? Well, we constructed a specific isomorphism that went from Z4 to U4. And so since there exists an isomorphism between them in our new terminology, that means that these two groups are isomorphic. And we also saw at the very beginning of last time's video that these two groups are really kind of essentially the same in the sense that, remember we drew the group table for Z4 and we also drew the group table for U4, and I even color-coded the two of them to try to highlight that those two group tables were identical under the replacement of the elements 0, 1, 2, 3 of Z4 by the elements 1i, -1, -i of U4. So to give kind of an analogy, it's almost like if I had a group where I called its elements lowercase a, b, c, d, and you had a group and you called its elements capital A, B, C, D, but other than that, those two groups behaved identically, then there's no real difference in content between our two groups. That's basically what's happening in this comparison from Z4 to U4, and I want to try to argue that that's really what's going on in general when two groups are isomorphic. So to try to unpack that into a more precise mathematical statement, I'm now going to state for you a theorem that says that if two groups are isomorphic, then how are they the same? Well, they share kind of all of the group theoretic properties that we've learned. So here's the theorem. So let G and H be groups, and let's suppose that they're isomorphic, meaning there exists an isomorphism phi from G to H. Then, first of all, they share the property of abelianness, meaning G is abelian if and only if H is abelian. And they also share the property of cyclicness, if that's a word, meaning G is cyclic if and only if H is cyclic. If one of them is cyclic, the other is too, and if one of them is not cyclic, the other isn't either. And then lastly, they share the property of how many elements they have of any given order. So namely, if I pick some number D, and I ask for the number of elements in the group G that have order D, that's going to be the same as the number of elements in H that have that particular order D. So these are a few examples of some of the group theoretic properties that we've met, and the statement is that isomorphic groups just are the same as one another in all of these properties. So let me prove at least some parts of this for you. Actually, part one of this is something that you'll prove on your homework. So let's start together with part two, which is the statement that G is cyclic if and only if H is cyclic. That's an if and only if statement, and so the proof should have two parts. First, we'll suppose that G is cyclic, which by definition means G is equal to the subgroup generated by some element, lowercase g. And our goal now is to prove that H is cyclic, meaning we want to prove that H is equal to the subgroup generated by some particular thing. And in fact, we'll do more than that. We'll say that H is generated by something specific, namely it's generated by the element phi of G, where this phi is our isomorphism from G to H. And how do you prove something like this? Well, this statement that we're trying to prove, that's an equality between two sets. And so remember, the way we prove an equality between two sets is by breaking it into two containments. First, H will be a subset of the subgroup generated by phi of G, and then vice versa. So let's flip to a new slide and start the first of those two containments. So first, just to remind you here in this blue cloud, our goal is to prove that H is a subset of the subgroup generated by phi of G. And how do we prove something like that? We take an arbitrary element in the smaller one, so let's let B be an element of H. And I'm going to try to argue that B is actually an element of the subgroup generated by phi of G. Well, what do I know about B? First of all, I know that B is equal to phi of A for some A in the group G. And that's because phi, which remember is our isomorphism from G to H, it's an isomorphism, and since it's an isomorphism, that means it's a bijection. And since it's a bijection, that means in particular that it's surjective. So everything in H is phi of something. And what next? Well, this A here, that must be equal to G to the K for some K. And why is that? That's because I've assumed that the group capital G, which is where A lives, is equal to the subgroup generated by this element lowercase g. So all of its elements are powers of G. Now maybe you can unpack that a little bit. So G to the kth power, that's G star G star G and so on. There's K of those G's in all. But actually you can break that up as phi of G star phi of G star phi of G and so on, with K of them in all. What I'm using to go from here to here is the fact that phi is an isomorphism, specifically that condition 2 in the definition of an isomorphism. So this now says that B is equal to phi of G star phi of G and so on K times. So that's phi of G to the kth power. And so look what we've done. We've shown that B is equal to phi of G to some power. That's exactly what it means for B to be an element of the subgroup generated by phi of G. And so we've successfully proven this one inclusion, H is contained in the subgroup generated by phi of G. Now we've got another inclusion to look at, so let's flip to a new slide for that. So for this reverse inclusion, I have to start from an arbitrary element in the subgroup generated by phi of G and prove that it's in H, but I know what an arbitrary element of the subgroup generated by phi of G looks like. It looks like phi of G raised to some power, which I'll call M. How do I know this is in H? Well, I know that phi of G itself is in H, because phi is a function whose codomain is H. But I also know that H is a group, which means in particular that it's closed, and so phi of G to the mth power is also an element of H. And that proves that inclusion. So we've proved both inclusions. That means we've successfully shown that H is equal to the subgroup generated by phi of G. That means we've successfully shown that H is cyclic. So what have we done? We supposed G was cyclic, and we proved that H is cyclic. And that covers that that implication of our if and only if statement. And, well, technically there's another half of the if and only if to prove, which is now we want to prove if H is cyclic, then G is cyclic. But I won't go through that because that's basically the same argument. just with the function phi that goes from g to h replaced by its inverse function that goes from h to g. And that inverse exists because remember we assume that phi is an isomorphism, meaning it's a bijection. Okay, so that covers point 2 of the theorem. I'll just say a couple quick words about point 3 before we end. So remember, point 3 of the theorem was the statement that the number of elements of order D in the group G is equal to the number of elements of order D in the group H. Again, assuming, as always, that these two groups are isomorphic. And so here's the rough idea of how you go about proving that. First, you have to prove that if I do phi of some element of order D in the group G, the result will be an element of order D in the group H, and same thing for phi inverse. Phi inverse takes elements of order D in H and sends them back to elements of order D in the group G. And once you've proven this, then here's what you can do. You can think about the set of all elements of order D in the group G and the set of all elements of order D in the group H. And what we've just argued or stated is that phi takes the set on the left to the set on the right, and phi inverse goes in the other direction. So these two functions are inverse to each other. That means that they must be bijections, because remember, a function is a bijection if and only if it has an inverse. So I've got a bijection between the set on the left and the set on the right. If there's a bijection between two sets, they have to have the same size. And that says exactly that the number of elements of order D in G is the same as the number of elements of order D in H. So that, at least sort of in sketchy form, proves the third part, and that finishes the theorem. All right, so long theorem, but we've finished it. So we'll use this theorem to help us detect whether groups are isomorphic or not in our worksheet for today. So I'll see you in class.